Welcome back to Introduction to Machine Learning. I'm Ludwig Botmann, and in this video, I will tell you everything about the ROC curve. So you should understand the ROC curve and be able to compute the ROC curve manually all by yourself. We will speak about the fact that the ROC curve is insensitive to class label distributions at test time. We will discuss the threshold selection, and in the end, I will tell you about the area under the curve. You already know how to evaluate a classifier by, for example, the ROC matrix. And now here in this chunk, we want to compare different classifiers, for example, in order to find the best possible classifier. We do this by using the TPR and the FPR values and plot them in a coordinate system so that we have this plot here, the FPR on the x-axis, and the TPR on the y-axis. Instead of using TPR and FPR, we could, for example, also use TPR and PPV, so true positive rate and positive predictive value, or in other words, recall and precision. But in this video, I will just show you the trade-off between TPR and FPR. So if you look at this plot here, you can see 3 points, C1, C2, and C3. And each of these points corresponds to one classifier. So keep in mind, these are 3 different classifiers, all of them trained on the same data set and on the same task. And now we can make pairwise comparisons of these classifiers. If we first compare C1 and C3, we see that C1 is better than C3, but why is that? Okay, so we are looking at TPR and FPR, and as you already know, we want to have a high value for a true positive rate, and we want to have a low value for the false positive rate. So the best value we could achieve is a true positive rate of 1 and a false positive rate of 0. So when we now compare C1 and C3, then we see that C1 has a better TPR than C3 because it's higher. And we see that C1 has a better FPR than C3 because the FPR is smaller. So the FPR from C1 is smaller than the FPR from C3. So in both of these evaluation metrics, C1 is better than C3. And so we can say that C1 dominates C3. Now we can compare C1 and C2. And you already can read that there is an unclear winner. Why is that? So C2 has a better TPR than C1, so a higher TPR, but C2 has a worse FPR. So the FPR of C2 is higher than the FPR of C1. So C1 wins in terms of FPR, but C2 wins in terms of TPR. So bottom line is that between C1 and C2, we cannot define a clear winner. Okay. This is the Rockspace, and we will use this in this chunk to compare different classifiers. As already said, the best classifier lies on the top left corner. So this one here is the best classifier because it has a TPR of 1 and an FPR of 0. So there is no classifier which dominates this one here. What else can we say about Rockspace? We can speak about this line here. And the diagonal is containing all the worst classifiers because these are all classifiers which produce just random labels. And I will explain you what random labels means, or better, why those classifiers which produce random labels lie on the diagonal. So if you think of these confusion matrices, so I will just draw a small one here. And if you then think that classifier randomly classifies an instance as positive with some probability, say 25%,
then it really doesn't care if the true class is positive, or if the true class is negative, because it's just doing this randomly. It hasn't learned anything. So let's say in that case, we have 25% positive predictions and 75% negative predictions. So what we get here are just two different values, A and B. So the absolute number of positive and the absolute number of negatives for the two classes. And then if you compute the TPR, it's just A divided by A plus B, but the FPR is exactly the same thing. So it's in both cases 25%. So no matter, the classifier will definitely lie on the diagonal here, and the exact position of the classifier depends on the probability with which the classifier is predicting the positive class. So to sum up, the best classifier is here in the top left corner, and on the diagonal are all the worst classifiers because they are just producing random labels. So what about all those, all the area below the diagonal? So what happens in this area here? And the point is, in practice, we should never obtain a classifier below the diagonal, because when we just invert the predicted labels, so we make ones out of zeros and zeros out of ones, then this will just result in a reflection at the diagonal. So a small example here, let's say we again have a confusion matrix with true classes in the columns and predicted classes in the rows, and we have, let's say, 4 absolute values here, A, B, C, and D. Then the true positive rate is just A divided by A plus C. And if we now change the labels of the classification of the prediction, then we change A and C, and we're going to change B and D. So what happens then? TPR new is just C divided by A plus C. And well, this is just 1 minus TPR. And for FPR, well, obviously you can do the exact same thing. An interesting fact about TPR and FPR is that they are insensitive to the class distribution, in the sense that they are not affected by changes in the ratio of positive class and negative class, at least at prediction time. What does this mean? So we have 2 examples here, example 1 and example 2. And in both examples, the true positive rate and the false positive rate are the same. So the true positive rate of first example is the same as from the second example, and the false positive rate of example 1 is the same as the false positive rate of example 2. But as you can see, the misclassification error is not the same. So we have on the left a misclassification error of 35%, and on the right side a misclassification error of 30%. And what is the difference between those 2 examples? So the difference is just the proportion of positive and negative class. So on the left side, we have 50 positives and 50 negatives. On the right side, we have 100 positives and 50 negatives. And in the terms of TPR and FPR, those 2 classifiers are just exactly the same. But if we would compute other metrics, such as the positive predictive value and the negative predictive value, these obviously would change. So keep in mind that at least at prediction time, TPR and FPR are insensitive to the class distribution. Of course, this does not hold during training. So for a different training data set, we will get different classifiers, different trained classifiers, and then the posterior probabilities may and will change. now we reach the very interesting and famous ROC curve. And on the next few slides, I will show you how to compute a ROC curve. So first, remember that usually our classifiers output scores or probabilities, or other way around, probabilities and scores. And if we want to have class labels as output, then we have to threshold those probabilities or those scores. And this threshold C here is in no way fixed. So we have to find, in the end, one perhaps somehow best threshold C. And what we do for the computation of the ROC curve is we just go with our threshold from 0 to 1. So we look at every threshold and compare the resulting classifiers. So for two different thresholds, we say we have two different classifiers because they predict different hard labels, even if the predicted posterior probabilities are the same. So how works drawing a ROC curve? First, we have to rank the observations on a decreasing score. Second, we start with threshold equals 1. So we are in the in the scenario of a probabilistic classifier. And with threshold 1, what happens there? So if you imagine you have here a 1, then P of x larger than 1, then we will have no positive predictions. So we start here in 0, 0, so we don't do any, so we have no true positives and also no false positives because we just have no positives. So all of them are neither true nor false. So we start in 0, 0. And then we iterate through all possible thresholds C. And so the threshold decreases from 1 until 0. And then we compute for each threshold the true positive and the true negative rate. And in the end, always something like this will happen. We go from 0, 0 to 1, 1, because in the end, for a threshold of 0, we will predict everything as positive. So we have a true positive rate of 1 and a false positive rate of 1, because we just have only positives. And the step size for going up is 1 divided by n plus, and the step size of going right is 1 divided by n minus. Okay, let's look at this in a practical example. So if you look at the table here on the left side, we have 12 observations. And if you count the true labels, the positives and the negatives, you will see that we have 6 positives and 6 negatives. And in the rightmost column, you have the predicted score of the classifier. So what happens now for a threshold of, for example, 0.9? So for a threshold of 0.9, we cut here between the first and the second observation, because 0.95 is larger than 0.9 and 0.86 is lower than 0.9. So we have one observation predicted as positive class, and this one is true, and all the others are predicted as negative class, so these are wrong. So what happens here is that we go one step up from 0, 0 to 0 and 0.167. So why is it 0.167? Let's clean here a bit. So TPR is just 1 divided by 6. Why is that? So we have 6 positives and just one of them is predicted as positive class. So we have 1 divided by 6. And the FPR is 0 divided by 6 because we have 6 negatives as well. And 0 of them are predicted as positive. So all of the negatives are predicted as negative class. So 4, 6, 8, 9, 10, and 12, all of them are predicted as negative class. That's good. So we have an FPR of 0 and a TPR of 1 divided by 6. And then we have a different illustration of what's going on here on the bottom right of the slide. And the data points in this plot are essentially the same as in the table on the left side. But I think it is a nice visualization to understand what happens here. Because what we are doing now is that we move with the threshold C from 1 all the way to 0. So now, right now, we are at 0.9. So we have one observation which is predicted as positive class, and all the others are predicted as negative class. So the background color always is the prediction, and the color of those triangles and circles is the true class. So if we go now to the next slide, you will see that the threshold C moved from 0.9 to 0.85, and the only prediction that changes is for this observation with ID 2. So this is a triangle, so it's a positive, a true, so the true label is the positive class, and now we are predicting it as positive. So now we have 2 positive observations, and we still have 6 observations which have the true class positive. So 2 divided by 6 is 0.3. And the FPR does not change because we didn't touch those 6 observations which are in fact have the true label negative class. So what happens now? We go one step up again, so 1 divided by 6 in the direction of the true positive rate, because we made another correct prediction. Then we go one step further and end up now between those 2 here. So we have a third one which was correctly classified. So now we have 3 divided by 6. So it's more or less the same picture. We just go up and up and up. But now, if we move the threshold further to 0, we have the first case where we have a true negative observation classified as positive class. So that's the first error in the negative class. So the FPR grows by 1 divided by 6. And so we go to the right in that case. And then we have again a positive, which is correctly classified as positive, and so on and so on. So let's perhaps on this slide have a look on the exact values of the threshold C. So we always have concrete thresholds, in that case 0.3, and perhaps you're wondering, okay, why is it 0.3 and not 0.31 or 0.35? And yeah, you're completely right. So it really doesn't matter where exactly we are between 2 observations. So in fact, instead of C equals 0.3, we could also say, okay, C is kind of element of the interval, 0.28 and 0.39. So these 2 values here, and every threshold between these 2 numbers will result in the same right step here, because we're just between 2 numbers, and between 2 numbers, all the thresholds have, for this classifier, the exact same consequence. So all those numbers of C on these slides are somehow arbitrary, but they are always between two of those numbers. So here, 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 and so on. So then we can go the last steps. So we jumped over some of the thresholds here, and now in the end, all of the values are classified as a positive class. So the true positive rate is 1, which is great. So all positives are correctly predicted as positives, but all the negatives are also predicted as positives, and of course falsely predicted as positives. So we have a TPR of 1 and we have an FPR of 1. And now if we want to compare different classifiers, so not only different thresholds for the same classifier, but different classifiers, then we can compare the ROC curves of those classifiers. And a very good ROC curve would look more or less like this. So it would go up and up and up, and then it would just go to right to the point 1 and 1. So the closer the curve to the top left corner, the better it is. If ROC curves cross, such as here the OK1 and the OK2 ROC curve, then we have no clear decision. So one of the model might be better in different parts than the other model. If we have small thresholds, what happens then? Then we will very liberally predict a positive class. So small thresholds are something in that corner here. And this would result in a potentially high FPR and high TPR. And on the other side, if we have high thresholds, then we are in this section here on the top, on the bottom left corner, where we conservatively predict a positive class, which results in a lower FPR and a lower TPR. Yeah, we cannot really easily select the best threshold. Visual inspection of all possible results seems useful, but of course, this is an important problem. So, because in the end, in a practical problem, we will have to decide for one threshold because we need a concrete classifier which outputs concrete class labels of the positive and negative class. So we will need later on some options to decide on the best threshold.
So how can we then choose the best threshold or operating point? If we don't know anything about class imbalances or costs a priori, then we will do this visually and in a post hoc analysis. First, we identify the non-dominated points, which are marked in the plot on the right side. So let's call those A, B, C, and D. And as a short recap of dominated points, let's look at point E. And E is dominated by both B and C, because C has a better TPR and the same FPR as E, and B has a better FPR at the same TPR as E. So A, B, C, and D are the 4 non-dominated points. And now we assess the TPR and FPR and decide which combo is best for the task. So there's no unique correct answer to this. So we have to look into our use case at hand and decide if it's better to have a false positive rate of 0.8 and a TPR of 1, or if it is perhaps better to have a FPR of 0.2 and TPR of 0.7, more or less. And then once we have decided visually for the best threshold, let's say we decide for B, we have decided for the best combination of TPR and FPR, then we pick the associated threshold. So we could go back to the last slides and just look which threshold C is exactly corresponding to this operating point B.
There is, however, a metric which allows us to compare different classifiers, and that is the area under the ROC curve. So it's just really, as the name says, the area under the ROC curve, here the blue area here. And Well, for a perfect classifier, we have an AOC of 1. It would be a classifier like this. And the worst value of AOC we can have is not 0, but 0.5, because keep in mind that the diagonal here constitutes of all the classifiers which just assign random labels, which is not good, obviously. And if we have an AOC which is below 0.5, then we should get a better classifier if we just swap the labels. So from 0 to 1 and from 1 to 0. And then we have an AOC which is larger than 0.5. The AOC also has a very nice interpretation. So it's not just a way for comparing two different classifiers, but we can really interpret the value of the AOC. So the value of AOC of, for example, 91.67% means that with a probability of 91.67%, the classifier will rank the positives above the negative observations. So if we draw a random positive and a random negative observation from the data set, then with this probability of 91.67%, the ranking of the positive will be higher as the ranking of the negative instance. And here on the right, you see a simulation of this model. And on the x-axis, the number of random draws from the probability distribution here. And as you can see, on the y-axis, we have the share of draws where a positive observation is ranked higher than a negative observation. So if I say number of draws, we always have to draw two instances, positive and a negative one. And then the share of the draws, if the number of draws increases, then somehow reaches here the value of the AOC.